So we've been talking about different components for a multiprocessor. The main component was the shared memory substrate, coherence consistency model. We also talked about some special purpose element for synchronization, for redundancy, and now we come back to a more general purpose component, the interconnect. You want to have multiple processors, you have to hook them up together. So what's wrong with using wires? Well, wires has been the solution we use to link together components, transistors, but this is a very old graph. As the manufacturing technology goes sub-micron, these are all nanometers, but still many generations in the past, the gate delays reduction is no longer able to counter the wire delays increase in latency. So we kind of found perhaps the minimum point if we use aluminum there, if we use copper somewhere along that line, but it's getting worse. The wire delay is getting worse. So that's a problem, and you might want to worry about it. This is a newer plot where we do include more nanometer regime, still not anywhere close. I'm just lazy, not generating a graph from raw data from Semiconductor Industrial Association roadmap. You can see local interconnect is not so much of a problem. It actually reduces as you scale. It's the global interconnect, the longer wires that matters, so you gotta pay a little bit attention. And there's the difference between whether you drive them with repeater or without repeater. Without repeater, it's worse. It's up here. With repeater, it's a little bit better, but this is log scale. Okay, so it is a problematic thing. Communication is more important in multiprocessor. If I have a workload, I'm separating them into components. So the more I separate them into multiple across many more processors, the per processor workload drops, but the communication workload increases. So that seems a pretty bad situation. So you got to worry about it. More communication, but the performance of the wire is getting worse. So what can you do about it? Well, I'm going to describe the conventional school of thought, which is, okay, you connect them with an interconnect. And I'll tell you more about my personal thought, which is a contrarian thought. It's not well accepted by the community. The community's been pushing all these different optimizations in packet switch interconnect for my conjecture for two reasons. One is that's what we've always been doing. We didn't really think about it very much, and to connect processors together we use an interconnect. And two, well, with an interconnect we can define a metric, we improve bandwidth, and that's easy. It's not necessarily very important, but it is one metric that at least at the highest level can factor into the performance calculation. So we're going to cover that, all the basics about interconnect. Primarily, what's the topology? Okay, you have to have a static component, how you link things together, mostly into these two categories, the flies, the butterflies, or the meshes or the toruses or tori, those type. Quintessential indirect network and quintessential direct network. We'll get into all of that. And the dynamic component of your interconnect is routing. How do you make the packet go once this static part is fixed? The difference between network and interconnect is mostly a notion of system. A network is the thing that connects multiple systems. Your internet, my computer, connected to your computer, totally independent computers, then the part that connects them is called the network. whereas an interconnect is a subcomponent within a system. So this system runs, let's say, one operating system. So we use interconnect, but most of this topology, routing, flow control, and these are really shared with the network community, not very different. Perhaps the traffic on these networks are different. So we're kind of going to use interconnect and network pretty much in an interchangeable fashion. So lots of this is well documented by the Daly and Tolles textbook. You can skip a couple of chapters. Again, like I already explained in class meeting with you, many multiprocessor textbooks do the perfunctory thing of using a small chapter and quickly cover these things. I think the Daly and Tolles textbook is far more detailed and information rich, so I strongly recommend you to read those. Even though they have many chapters, they're not that long, so it's not that big of a deal to go through them. When we have a multiprocessor, especially a scalable one, we want to put them together, and sometimes we have the dense hall organization where we do have individual elements, memory and processor. Most likely they're all packaged together, okay, with some controller forming a node. So that's how it plays into the overall architecture of a multiprocessor. You have to have those, and we're going to study the part that's relevant. So first off, we're going to use a lot of terms, and let's just define them here. Again, the textbook did a much more thorough job about this. So when I think about network, I like to think about this general sort of notion, this logical diagram. I have these nodes, and that would be just like in a graph. There are nodes in the graph or vertices, and when you connect them together, those are edges in the graph, and they're called channels in an interconnect or network. So for instance, if I have 4 nodes, or let's mark them, not 4 nodes, 9 nodes, a 2 by 2, so I may have a mesh that looks like this, right? So clearly that is a node, this is a channel. Conventionally, there are 2 types of possible nodes. One is called a terminal node, and that is the node that initiates traffic, or is the ultimate destination of traffic. Think about your computer on the network. And there are other nodes on the network whose job is merely to relay the traffic that we discussed. Okay, so if you have those cases, like an internet, you have dedicated routers just forwarding traffic from one part of the network to another. It's called an indirect network. If all your nodes are terminal nodes, it's a direct network, and we tend to see direct network in a multiprocessor system, and we just interconnect them together. But sometimes we can use dedicated router to always go through them and then come back in a larger scale machine. So the traffic are going to be packetized. We're not sending streams of things. This is not a bus, I shouldn't say bus. It's not a dedicated connection. One node keep on pumping stuff on it. It's all broken down into a packet. And in a multiprocessor, in the context of a multiprocessor system, they tend to be very simple. Not a whole lot of different packets as in TCP/IP, but very short and small number of the predominant type are data packets and request packets. Request packet can be very small. They're just a few bits on top of some address, that you need, you send it from this node to the home node to say, I need cache line X. And when the data comes back, it's a data packet with some metadata with it, but predominantly the payload is a cache block. So these packets are not long. They're not like Ethernet packets, kilobytes, but really 128 bytes if your cache line is about that long, or even smaller, 64 byte, give or take, mostly longer than that. So packets can vary in size depending on what type they are, but from the network's point of view, we want some uniform system. So there's the notion of a flow control units or digits or flits. Okay, so these are like containers. You can have a standard size, and if you have more traffic, you use more containers. Sometimes you might even hear a different word, which is a physical unit or fit. A fit is how much you can transfer in one cycle. So if I have between one node and another a channel consisting of 4 wires, and they run at gigahertz, okay, and I'm not using any fancy scheme, it's just it's just NRZ, non-return to zero. So every baud I send, every cycle I send 1 bit per wire, and this is going to give me a fit of 4 bits. Okay, so that's the unit transferred in one cycle. But that may not have any significance. So maybe every time I have to send 32-bit. That's the minimum unit. Then that 32-bit would be my flit. And my packet is independent of the network design. If I have a cache line size of 64 and I need some extra bits to describe as header, I may end up having an 80 byte packet. And that at 32-bit per flit, that would cost me 20 flits to transmit my cache line. Okay, so these are the notions. We are probably going to use flit more than anything else. So why do we care about networks throughput? Because it impacts. You'd think if I have a request, I care about the latency. When can I get the result? Okay, so there are 2 parts to that. We'll unpack this completely just in the next slide. But one part is related to how fast you can propagate the signal. Okay? And it's limited by the speed of light. So in a very far away node, it takes a while for the packet to be possibly arriving at the destination. But there is another part that we can control, and that is the bandwidth. And serialization latency is related to bandwidth. Okay? You can think about it as if I have a narrow pipe, then a fat message. If I have a long message, okay, and I squeeze through this one single wire, and it will just take longer, and that's the serialization delay. It's the size divided by the throughput of that channel, and that's how long it takes from the beginning of the message to the end of it to go through. So by increasing network throughput or bandwidth, I reduce network latency. And out of different measure of bandwidth, there is one that we cared about most, simply because it's a nice one-number summary of a network. So just like when you're buying a car, let's say you care about its engine, they may quote you a horsepower number. And in a network, if you want to get one number to characterize it, it's usually the bisection bandwidth. And the idea is roughly you break the network into 2 equal parts, and what is the overall bandwidth between those 2 parts. We'll show you in a bit why we care about this. So let's go back to what we care about from a transaction point of view. I have a request. How long is it going to take? well, it's going to take some time. Let's say from one node over here, node A, to node C, let's say. So what is the path of that packet? Well, if you think about it, my packet, let's pretend it has two flits, 1 and 2. And this little following animation shows you what it does. And at every node, we go through a router. And I'm showing just a direct router. This is on a chip with 4 cores, if you wish, and I'm connecting them with a mesh or a ring, whatever you think about it. This is just one example. So to interact with that network, I have wires, but these wires need to be managed. So that's what the router does. It needs to compute the route, decide which packet go through, allocate the resources. We'll get to all of that detail, but for now, just understand that this requires processing, and it takes a pipeline. So that's what's happening here. There's a 3-stage pipe, and it will take 3 cycles just to process it. Okay, later on we will see that a canonical pipeline takes about four stages, but industrial implementation tend to be even longer than that. But in theory, you can reduce this to 2 or even just 1 cycle in the ideal case. So after one hop, the processing of one router, you would go into the wire, and that has propagation delay. So this goes on like that, and eventually it will be propagated to the end. So if you want to measure the total delay from the beginning of the very first bit to the end of the very last bit of my packet, from the beginning of the first bit that I send to the last bit that I arrive at the destination, the total delay is summarized in this formula. It's fairly straightforward to think about. The first term says how many hops I need to go through. Okay, so this is a hop from one node to another. This is a second hop from another node to finally a third. So every hop I need some router delay, and that's TR. So the average packet delay is, of course, the average hop count times the router delay, and that's how much I spend in these routers. That's processing delay. And then you have the wire delay. Okay, the wire delay depends on the speed of propagation, and somehow people like to call that velocity. My pet peeve is they have no idea what they're talking about. Velocity is a vector, so if you're just using it as a scalar, you should call it speed. Okay, using velocity is just bad taste. But anyway, this is usually how they chose the symbol. The average distance, how long is this wire, how long is that wire, your average length, wire length, divided by the speed of propagation, that's your propagation delay. So it may be very fast, it may be half a cycle, but this is the minimum you have to incur. Finally, this can be thought about as the head of the train, right? Number 1, the head of the train would take this long to arrive. And then how long will it take for the entire train to arrive? Well, it depends on how many cars are there in your train, and that's the serialization delay, the total length of the packet divided by the bandwidth. So if I can process 1 flit a cycle, then my bandwidth is 1 flit per cycle, which can be translated into gigabits per second. And my packet length is fixed. So that's how much delay I'm going to get. Okay. Now, if you have a simulator, you can model everything, and you can get exactly how long it takes for a particular packet, and perhaps get a distribution and go on and analyze what's happening. But in many cases, the community of at least the network community likes to think about this in abstract terms and manipulate formulas. So that's nice. And then we have all these different additional things to use as tools to reason about our network. And one way to think about this is to think about traffic patterns. Now let me draw a little example. This would be an oversimplified example. So suppose I have a network of just the one that I was showing before. Choose brighter color. I have 9 nodes. This is my network. And okay, let's use a slightly different color for the channel. Okay, I have this. Right. Now I want to think about what happens to this network. The first question I may have is, when will it saturate? That means I cannot take more traffic than that. Okay. How does that work? Well, to reason about that, you need to know what the traffic pattern is, because it depends. Let's say each of these channels is has a carrying capacity of 1. Okay. Now your question is, when do I have a network saturation? Well, you saturate when the busiest channel is completely filled. So the question is, then, which channel is my busiest channel? That is the notion of a traffic pattern matrix. So let's give this guys some number: 0, 1, 2, 3, 4, 5, 6, 7, 8. So my traffic pattern can therefore be described by a matrix. Okay. What is this matrix? This matrix tells me the intensity of my traffic from source to destination. So call this matrix big lambda, and each element is lambda s source to destination. So let's have an example. Let's say I have an unfortunate traffic pattern. Everybody talks to 2. Okay. So 0 sends packet only to 2. And so on and so forth. So we'll see the traffic pattern is 1 for that column, but nothing else, 0 everywhere else. No, I have that. Okay, how does that matter? Well, it matters because now I can, based on my routing algorithm, I can know how 1 unit of source traffic would result in 1 unit of load on a particular channel. So to kind of visualize this, let me try to draw a 3-dimensional view of this, right? So I have my network over here. But this is just sending and receiving. They don't, or relaying. They themselves, the router themselves, do not really generate traffic. So where does the traffic come from? They come from whoever is attached to this. In our case, this would be a core and its caches and some controller, right? So this would be our node. And it's the core that generates this traffic. So every one of them has this thing on the 3rd dimension that is to be blamed for generating the traffic. Okay, so let's say this is node 0, that's node 2, and we all want to send to node 2. So if I drop 1 unit of traffic on node 0, how many units of traffic do I get on all these channels that I'm seeing? Well, it's 1 unit here, 1 unit here. No, very, very clear. So what if I drop 1 unit of traffic on node 1? Then it's another unit on this channel. So now, are you following me? If I do this exercise for everyone, then I get all the channel load on every channel, and then I find out the most loaded channel, and it might be this one. Okay, so maybe for every 1 unit, so you can imagine there's a constant alpha associated with this, right? This indicates intensity. This may be, I don't know, 1 flit per cycle. So if I have a traffic pattern of this, and the intensity is 1, then I didn't finish this over here. But let's just say, you know what, let's be exact. Let's say this is my traffic pattern, that I don't have anything else. Okay, it's all 0. Okay? Just these two. Everything else is 0. Then that's my load matrix. In the end, my channels load is 2 on this unit, 1 on this channel. Okay? So then I would know the channel with the most traffic is this channel, and if this channel can support 10 flits per cycle, then under this kind of pattern of traffic, I can support a constant of 5. And then this network will just saturate. So this is basically a summary of what we were just doodling on the screen. If we measure the channel's demand, any channel, let's say this channel over here, the channel demand relative to what you drop on the source, and we call that ratio gamma. So if I drop 1 unit here, on average, I get 2 unit here, then gamma would be 2. So this is the ratio, and every channel would have a gamma associated with it. The channel with the most traffic, of course, would have gamma max, and that determines the network's throughput. And when the traffic reaches the throughput that we can sustain, then the bottleneck saturates. So it's quite clear. The channels, every channel has a throughput of B. You cannot go beyond B. And since this is your load, let's say this is 2, that means if you have half a unit dropped on the source port, my throughput, my bottleneck channel will already saturate, and therefore my ideal per channel throughput is half. Now, this ideal throughput is traffic pattern dependent. It depends on your matrix. So if we describe a network, we cannot have this number. We have to specify it's this particular network and this traffic pattern. So sometimes people use the uniform random traffic, and the matrix is just this. Everything is the same, and then the ideal throughput, again per channel throughput under the uniform traffic, even has a special name called capacity, so if you want to use the jargon. So if we take an example of so why bisection bandwidth is useful, it's usually those are the channels that are most loaded. So let's take this example. If you have mesh with uniform random traffic, then for each unit of source traffic. Again, if you drop 1 unit at any source node and they start to send to wherever, to the destination, you can figure this out. About half of the packet would cross from this side to that side. Okay, and same thing, half of the traffic, half of the packet, these nodes, these half of the nodes sent would cross the bisection bandwidth. Okay, and it so works out that for every unit that you drop, 2 units of traffic land on these bi-channel bandwidth, bisection channels. Okay, there are these many bisection channels, and as a result, the capacity would be half of the channel bandwidth. In other words, if this can support, I don't know, let's say 10 gigabit per second, that means if my source, my processors generates 5 gigabit per second and it's the traffic pattern is uniform random, then I saturate. In reality, we never get to the bisection bandwidth. If we get to that traffic, obviously we saturate. So beyond that traffic, that's x-axis is traffic, bits per second, whatever is the unit. It's the traffic offered, meaning it's the source, it's the client. Again, in my multiprocessor, this is simply requests and data from the processor's perspective. And y-axis is showing my latency. So you see, if we get anywhere close to that, I'm guaranteed to have infinite latency. I cannot handle it. Okay, so this is for random traffic, by the way, and in reality we don't get that. We get something worse. It's unbalanced. It's not uniform random. There are hotspots, so the saturation throughput, the goalpost moves inwards, and even that is too ideal because sometimes you have channel idles. So really the saturation throughput is somewhere even lower, beyond which your latency is infinite. What about latency? Well, the minimum latency, we just calculate this quite a while back, right? So it's the average hop times the router delay plus your length divided by the bandwidth. That's the serialization delay. This means if you have a completely unloaded network, that's your minimum latency for an average packet. Okay, and in reality, you get a little worse than that. So T0 is what is observed as the minimum latency. And you will generally see a curve like that. As we increase the traffic, there's going to be more congestion, and the packet would have to spend more time waiting. And that is an important issue in terms of the overall system performance. We care about the latency. We don't want the network to be oversaturated, so my requests won't get there. So in the next couple of videos, we're going to explain the details about how a packet get routed, but this is something to keep in mind, and that all the design decisions, like the throughput or the bandwidth of the network, really ultimately impacts the latency of your transactions.